Hello, this is Jonathan Templin, and this is an online lecture that is an introduction to models for binary outcomes or logistic regression. This is a lecture that is fitting in after our overall discussion of generalized linear models. So it's going to include part of an example that had shown up in the previous lecture. But this lecture really is to describe what happens to logistic regression, what types of scale the parameters happen to be on when they come out of the computer, how we convert that scale. The scale, first of all, is in log odds or logits, which is an odd one, but we can convert that into probability or odds as well. And then further, how to talk about interpreting main effects, unconditional or conditional, simple main effects, and interactions. So, generalized linear models for binary data, logistic regression. Turns out these have a lot in common with what we do with conditionally normal data. Our regular general linear model, the regression ANOVA that you're used to, these will almost look identical to what you end up getting from those types of models with several key exceptions, and we're going to get into that. We're using data from UCLA to make this happen. I have up behind my slides here, I have R that has the data and our example built in so we can see how it is coded. So you're welcome to follow along as well. To do this, we're going to make use of the Ordinal package, which I'll talk about in just a moment. So the data come from 400 college juniors that were looking at factors that were influencing their decision to apply to grad school or not. The data directly have three levels of the outcome. So our outcome is this y that happens to be the likelihood that a student may apply to grad school. Students originally were allowed to rate this with a 0, meaning unlikely, a 1 meaning somewhat likely, and a 2 meaning very likely. But to simplify this analysis, to introduce the topic of logistic regression, we're going to combine 1 and 2 together so that a 0 still represents unlikely, and that a 1, so these are now going to be equal to a 1 represents the, a 0 is unlikely. A 1 represents a student who is somewhat likely or very likely. So we'll just say likely to apply to grad school. You typically wouldn't do this in practice. You would use a multinomial distribution, which has two or more than 2 categories. Actually, it's 2 or more categories, but it just complicates the analysis just a little bit as we go forward. Now, predicting this, we're going to have a parental education variable, whether or not this is a 0 or 1. A 1 indicates whether or not one or more parent has a graduate degree. One more parent of the student has a graduate degree. We're going to have an indicator variable for public education, so whether or not a 1 here represents a student attends a public university, and a 0 represents not a public university. And finally, GPA is a grade point average on a scale of 4. So this is your typical GPA that we have here. We're actually going to center GPA at 3. So we're going to take GPA minus 3, and we're going to call that GPA 3. And again, we're doing that because centering is important, helps define some of the parameters, and it certainly is important when we get to interactions because our simple main effects depend on 0 for the interaction. So we want 0 to be a meaningful value. And centering at 3 means our 0 point is at 3 for GPA, meaning a person with a B average. You compare that with a person with a 0 GPA, an absolute F average, which most likely doesn't exist in college juniors. So here we have our data, some descriptive statistics of the numbers of people and the frequency. Here you'll see there's about 45% of our students are looking to apply versus 55% looking not to apply. And what we're going to end up doing is using a logistic regression, meaning the outcomes themselves will be converted, or pardon me, not the outcomes. We're not touching the outcomes. We're not doing any transformation on that. What we're doing is transforming our model parameters onto a scale that is much more continuous. So what we want to have in the logistic regression is we want our predictors. Remember our beta 0 plus beta 1 x. This thing has to be, this is called the linear predictor, and it has to follow, has to range, oh, that's not good. What am I doing? Get rid of that. This, really we want this to be between negative infinity and positive infinity. And for whatever reason today I can't draw infinity, so my apologies on that. So to do that, we take for each person. The mean is the probability. Sometimes we call that pi, but the probability y equals 1, and we're going to take the log of the odds of that, right? So y equals probability natural log of that right there. I'm going to set that equal to beta 0 plus beta 1, or however our model looks. Now, when we do that, the scale of the parameters, what the betas are on, is something called the log odds scale, or Logits scale. That means beta 0 and beta 1 also range between negative infinity and positive infinity. So because they're in Logits, they start to lose a little bit of their meaning, or they're really hard to describe with respect to data, and that's what this window right here is trying to represent. By the way, let me just pull this up. Check my voice. Yes, it's still working. Okay, good. So what are we talking about here? Let's see. If we get a parameter value with a beta of 0, or we get a predicted value, so we form a predicted value from this, and we see the logit is 0, what that means, what that corresponds to, is a probability of 0.5. And you can sort of see how that works, right? Probability of 0.5 over 1 minus 0.5, the log of that is really the log of the number 1, and that has to be equal to 0. The log of 1 is 0, always, in all cases. So therefore, that's how that works out. Now, the other part of the logit is that as you go up above 0, that means a probability. So this is like the 50-50 point right here. Anywhere above 0 really corresponds to a probability between 0.5 and 1. And that probability between so you can see it right here on the y-axis. And the curve, the logit, sort of asymptotes at 1, right? So it cannot go above 1. So if we were to look at a probability of 0.9, that corresponds to a logit of 2.2, right? So it's just right up here. Now, the other nice thing about logits is they're reflective about kind of this 0 point, or this kind of this diagonal here, in that the top line and the bottom line kind of correspond. What do I mean by that? If you take 0.9, the complementary probability of 0.9, or 1 minus 0.9, equals 0.1, right? So the sum of 0.9 and 0.1 equals 1. The complementary probability is negative 1 times the other logit, right? So where 0.9 was 2.2, 0.1 is negative 2.2. So it's reflected about that 0 point, or that 50-50 point. Now also, when logits go up, there's a sort of a finite place where probability starts to get increasingly close to 1. It never really touches 1 until you get to the asymptote, though, or the infinity. So really, a logit of 4.6, which is all the way up here, represents a probability of 0.99. Right? So we can keep going and going and going, but we're only, the logits themselves can be any number. They can go up to positive infinity. But in probability sense, once you get past 4.6, you only got 1% left of a thing happening. That's really not a whole lot left. So when you see a 4.6 as predicted value, you have a pretty good certainty that that event is going to occur. So the question I have asked you right here to think about is, can you guess what a probability of 0.1 would be on a logit scale? Well, 0.1 is the complementary probability to 0.99. You add them together, you get 1. So therefore, the 0.1 has to be down here, and it's a negative 4.6 for what that is. Okay, so the nice thing about this is that what we're doing with logistic regression is having our linear predictor predicting the logits, right? So we have a predictor here, we have a logit value. This graph on the left is what we would think about with a linear regression. But when we convert this back to probability, right, we take E to the predictor over 1 plus E to the predictor, we get a bendy or curvy line that asymptotes at 1 and 0. So the nice thing about this is that you can talk about it with respect to probability for most types of analyses, particularly predicted values. Predicted values are very easy to talk about in probability because you're talking about the predicted probability an event occurs. Now there's a set of terms that you cannot use, usually differences, like mean differences and so forth, because the probability will depend on where you're at on the scale itself. So you can't easily use probability to describe differences in means or differences in parameters. That's where we typically use odds, but I'll show you that in our example. So when we put it together, here's our empty model. Like we would have in linear regression, if we were to have an empty model, it just has an intercept. And as you saw in linear regression, the intercept gives us the mean of our data. Hooray! So the same thing happens in the logistic regression. We just have an intercept. You note we don't have error here. Right? There's no error. Nope. And that's because error does not have a spot in the distribution that we're using. The logistic regression assumes a Bernoulli distribution for our data, our outcome. And so the Bernoulli distribution, often known as the B, and there's usually one parameter, a P, is P to the event occurring times 1 minus P to the 1 minus the event occur. That's its probability mass function, PMF, or often I just call it a PDF, right? Plug in P and Y, you get the height. That's how it works. But because of that, there's only one parameter. So once we model that parameter actually happens to be the mean. Once we know the mean, or probability, if we take P times 1 minus P, we get the variance, which is what error variance would end up doing anyway. So in a logistic regression, error variance doesn't really exist. It does, technically, because it's wrapped into the mean, but it doesn't show up on the model line like we had before. So, because of that, we have this interesting set of equations that don't have error involved. It just is a model for the mean that we're showing. Now, there are places where we can actually start to quantify this, particularly when you get to multi-level models. If you have a multi-level model with a binary outcome, you've got maybe students nested in classroom or time nested within person, multiple observations from the same person. You can use, you often want to get an estimate of that level 1 variance, and turns out it actually happens to be 3.29 always. The reality of why that is, though, is beyond what I want to talk about for this course. It's just sort of a statistics piece of trivia. Impress your friends with that knowledge. So let's get into logistic regression in R. We're going to use the Ordinal package, because the class of models that we're using is something called Ordinal Logistic Regression. So the beginning of my R syntax that you'll find right here, we'll install and load this for you if you want to follow along. We'll also have our data that's saved in the Logit file right here, so I'll read that in with the read.csv, and you can see all of that. The other part that I have in the sort of the beginning part of my R script is transforming all of the data and computing the descriptive statistics that we saw before. In the Ordinal package, the function that we'll use for binary logistic regression is the CLM function, which stands for cumulative linear models. The word cumulative and ordinal go together because if we had more than one category, the probability that we'd have for that variable would be a cumulative probability that we're modeling, which makes certain constraints in the model that, again, we don't really need to talk about for the specificity of this lecture, but that's sort of where to begin in the process of modeling categorical data. And for that matter, by the way, we could teach an entire class on modeling categorical data. So we're just scratching the surface here. I just want to give you the idea that it exists, that we can do it, and actually there'll be a homework assignment on this too. So when we unpack the CLM function, here is what we end up having. You'll see that the CLM function, first of all, the thing that we have to do with our data to make it work here, or at least our outcome variable was going to be lapply. So if I show you my data, you'll see here's the apply variable. That was the 3 categories that came from the data directly, and we converted it into a 0 or 1 variable. But what the function wants us to do, the CLM function, is that the dependent variable has to be saved as a factor format in R. And again, remember, factor is R's way of coding up a variable. It allows it to effectively go and describe the number of categories that happens. How we do that is we put the dependent variable enclosed in this factor function right here. And we set it equal, I'm setting it equal to a brand new variable at the factor. If I show you what the content is, the variable is, the way you can tell it's a factor is at the bottom it says the number of levels in the data. So the factor actually goes through all of our numeric responses, or even our alphabetical responses, we put that in the factor as well, and it categorizes them in order from lowest to highest. Right? So it says we have 2 levels, a 0 and a 1, and that's what this function is going to use to describe our data. Now, getting into the data itself, what you'll see here, or the function itself, is that, again, it's going to look very similar to the LM function in that at the beginning, we have this lapply dependent variable. We put a tilde in between it and the predictors, and for the empty model, we just put a 1 there. That 1 represents the intercept. When you put a predictor in, it's assumed that a 1 shows up, but you can still put the 1 there if you'd like to. We tell it our data. And then this last option, you don't actually have to run or to use. I'm doing it to emphasize that this is a maximum likelihood algorithm. So what this last option will do is turn on the iteration history. The computer is effectively guessing and trying to figure out the best parameter values that maximize the likelihood that goes with this. So again, we're very close to what we saw in our LM function to begin with. So let's make this thing run. Let's fire it up. Here goes our model. You'll see the steps it took. We have iteration 0. Its first parameter was a 0, it guessed. Remember, we only have one parameter here. It's this, what we would call an intercept right now, although there's a little bit of an issue with that coming up. And then we see all of our other values that go along with this as well. But the cool thing, or the thing that you really want to see, is this last line right here. Optimizer converged. Well, those are words that you don't use often, but you can tell everybody how happy you are when your optimizer converges. They'll look at you funny. The absolute and relative convergence criteria were met. That basically means we found the peak of the likelihood function for this analysis, and so we can use these results, is what it's telling us. When it converges, we can use them. If it doesn't converge, we have a problem, but hopefully that won't happen very often. So let's take a look at our data, our output. We can use the summary function to show us the output. And now at the bottom here, we see the threshold coefficient. So we actually, let me just go over to my slides again. This is a picture of what you see in R. In here, you get kind of a two sets of information. The first bit of information, this is sort of a model fit, we'd call that. The model fit information tells us how many observations we have. I like that abbreviation, knobs. And here we have a log likelihood. The log likelihood is the peak or the height of that curve that we just found to figure out what's the maximum at. That log likelihood gets used for model comparison. This is the form that we use that to form likelihood ratio tests, although we're going to let R form those for us. It tells us a little bit about the, this AIC represents what we use to compare models that are non-nested. So likelihood ratio tests are for nested models, and these are non-nested models that use the AIC for comparison. It tells us how many iterations it took and a little bit of technical information about what the end of the analysis happened to be. But then it gives us our parameter estimates. And what you'll see begin with is it calls this a threshold coefficient. What is a threshold coefficient? Well, it turns out the way that categorical data get coded in a lot of their algorithms is often backwards somewhat. You have to kind of look through the manual or do what I'm about to do to guess and check this. But really what this is not the intercept as we would see. It's actually 1 minus the intercept. So you have this, or pardon me, negative 1, 1 minus the intercept, negative 1 times the intercept. My goodness. That is how we end up getting the intercept back. So this is really not exactly the intercept. And you have to remember that because when we start to do our model comparison, if we want to use GLHT, the thing that would give us our linear combinations, to go make a predicted value the way that I'm going to show you, we want to keep that at negative 1. And so that is how it comes out. Now, how did I figure that out? Well, I looked through the documentation and I found the equation. But in lieu of that, here's how you can quickly tell. What you can do is figure out how does this translate if we turn it into a probability. All right? What is the probability associated with that? Because that probability should match up with the mean of our dependent variable, right? So let's go over to R and show you how that works. So what we can do is we can take E to negative 1 times that coefficient. That's what shows up in that highlighted part of my code there. Over 1 plus that same value, we get a probability out, 0.45. If we wanted to compare that to our data, we just take the mean of our data and see it's 0.45. Now, you'll note to make the means match, to make the intercept meaningful, I had to put a negative 1 out in front. So that's how you can figure this out. So why I use the empty model in a categorical analysis is because each algorithm does it slightly differently, and it's maddening. It really is frustrating. I'm telling you this as a person who's used these algorithms for years, and they still frustrate me. So really, you want to use the empty model to orient yourself as to what direction the data is modeling. Technically speaking, the threshold, the number that comes out, is a probability of the opposite event happening, or a probability of a 0, like when we convert it to a probability. So that's where the -1 comes in. Okay. So knowing that, we know that our threshold was 0.207, so our intercept was actually -1 times that. So is the predicted logit. How we interpret this number is in logits. It's the predicted logit of the probability that y is 1 for an individual when all predictors are 0. So let's put that into the actual context of this example. We take the probability that someone is likely to apply to grad school. The log odds of that probability is given by -0.2007. So here, typo, because of the empty model, this becomes the average logit for the sample, or the average, right? So if we want to convert that back to a probability, we just use this same example over here, and you'll end up seeing what happens. So the log likelihood we saw was -256.26. Again, these two numbers, log likelihood, AIC, we don't typically interpret them much at all with a single result. That being said, there are people who would say this is sort of how far off from perfect model fit there is, but that doesn't really give us much of an indicator. It's a relative statistic based because the likelihoods are relative things. So the other thing we could do is we could convert our intercept into probability. We just did that. We could also convert this into an odds. So the odds of applying, remember the odds, if I were to call this probability right here, the odds of likely to apply would be given by prob, the probability of applying, over 1 minus that probability, right, or 0.818181, whatever. We can actually find that directly from our data or from our analysis if we just take e raised to the coefficient we're after. So these happen to give us the same value. And what that tells us in general is that the odds of applying to grad school, because that probability is less than 0.5, remember the odds, something that's a 0.5 probability, a 50-50 chance, is what we call even odds, or the odds is 1. The odds of it happening versus it not happening is 1. When the probability shifts below 0.5, the odds become less than 1, and that's why you see this happening. So it's less as likely, or 80% less likely, or I guess 20% less likely to occur than you see. So here we see the logit. Our predictor effects are called linear and additive, just like in regression. All right. Odds. The problem, though, is what does a change in the logit mean? It's sort of detached from what people understand about data. So we can bring it back a little bit by talking about odds. We can also bring it back by probability. We can't add probability, that's for sure. We can't do the same type of effects with it. But typically what we'll do is form kind of the combination we're after in the logit and then shift that either to odds or probability depending on what we're after trying to describe. So let's add some predictors to this model. I'll show you how it works. So here, how does this look? At the beginning, this is our linear predictor. We're going to use it to predict the mean of our outcome, or the probability that someone applies to grad school. Oftentimes, we can just use this as our model to describe it. We just don't have error on it. We're going to predict it with main effects to begin with. Parental education, mean centered, or GPA centered at 3, and whether or not a person goes to a public or private school. So now, with that, you can also express this model similarly down here, where we say this model is for the same model for the logit is given for the probability. Right? So this is the probability is e to the logit plus 1 over 1 plus e to the logit. Again, once we know the probability, we know the variance, and that's how that all works. So let's go back to the syntax. I put in my 3 predictors, parental education, public, and GPA 3. And I go and I just noticed that public and GPA 3 are switched here in this example from what I showed you before. So this would really be beta 3 over here and beta 2 over there. So we run this analysis. You could run it in R. You see it converge. Also converge in four iterations, which is just coincidental with the last one. You can also see how the parameters change. These are the guesses for each of the betas that the algorithm is making at each point of it trying to find the peak of the likelihood. And the first question we have to ask is whether or not this model with predictors fits better than the model that has no predictors. Or, another way of putting it, we have two models. One is a null model, one is an alternative model. And as we talked about in the maximum likelihood section of the course, the alternative model, the null model is nested within the alternative model, meaning that the alternative model contains the same amount of information and can get back to the null using some type of constraint. So basically, if we take beta 1 equal to beta 2 equal to beta 3, in our alternative model, when these are all 0, that knocks out each of these terms, making our alternative equal to our null. So when we do a model comparison here, we're testing the hypothesis that at least one of these beta coefficients is not equal to 0 simultaneously. This is like a simultaneous test, an omnibus test, if you will. You can see an analysis of variance, although these are different types of variables. So that's the null hypothesis. The alternative is that at least one's not equal to 0. The way we test it is the ANOVA function in R. I love this function. It makes it so much easier to do. Let me show you a little bit here rather than just going straight to my slides. If we run model 2, we plug in model 1 and model 2, and this is what we get out of the computer. We get this likelihood ratio test, which is our new version of an ANOVA table. We won't actually have ANOVA tables anymore. There are no sums of squares. There are no mean square when it comes to logistic regression. So now, here's the table that I just showed you. The test statistic is given by this LR stat column, right? Which is -2 times the difference in the log likelihoods. Here's the log likelihoods. Let me see. This follows a chi-square distribution with degrees of freedom equal to the difference in the number of parameters, or the number of parameters involved in this null hypothesis. So there's 3 degrees of freedom. The p-value associated with that is over here. You can tell that's very small. So similarly, like you would have in any other hypothesis test, we reject our null hypothesis, and we assert that at least one of those parameters is not equal to 0. So by doing that, we show that we reject the null model, we reject the empty model, and we say that this model is preferred to the empty model. Moving forward, here what we do is we have to look at the parameter estimates from the summary statement. Again, we have our threshold coefficient down here. Remember, this is the intercept equals -1 times that threshold right there. Right, so if we take -1 times this, we can interpret the intercept. This happens to be the predicted probability of the value of the logit for a person who intends to apply to grad school, who has a 3.0 GPA, right, when all the predictors are 0. 3.0 GPA at a private school with parents who did not go to grad school themselves. And again, we can convert that to a probability. We'd say that a person who fits these conditions the probability they apply is 0.417, 42% chance they apply to grad school. Similarly, this is actually par ed variable, par ed. This is a regression slope. Right? Or pardon me, in this case, because par ed is a categorical variable, this represents, we would call this a mean difference, right? Or a difference in the logit between the person who has parents who went to grad school and a person who has parents who did not go to grad school. So what does this refer to? Well, this is just, we interpret this the same way as we interpret a regression coefficient, but instead of saying it's the data, we call it the logit. Right? So for every 1 unit change in the variable it multiplies, in our case, the difference, this is the difference in predicted log odds of someone who goes to grad school versus someone who doesn't. Now, you might be saying, let me go convert that to a probability. That's where the problem comes in, because that probability depends on the other variables. To convert the probability, you have to go and you'll figure out what those happen to be. We know that the logit difference is always the same, whether the other variables are in or out, because the logit difference comes from the difference in the parameters. Right? So, probability doesn't typically work. What we have to do is usually just take e to that number, 1.0596, to tell us the odds. The person is more likely, or the odds ratio, how much more likely a person is to apply based on that. And that's actually what we're going to see here. So, we can't really do that with probability as easily, because again, we have to go and condition on the other variables. Probability, here in this case, gives us a predicted value. And to make a predicted value, we have to know the values of all the other variables themselves. And that difference in probability depends on what those values happen to be. And it won't be constant because the scale S-shaped curve here. If some of our predicted values give us a predicted value here, the difference in probability will be that much. But if we're down here, the difference in probability is much smaller. So we really can't use probability to talk about differences. But I'll show you a couple examples here. So in odds ratios, let's go and form this. So let's imagine we have a person who has parents who have a graduate degree. So par ed equals 1. Right, for this person right here. But for this whole slide, let's imagine GPA equals 3 and public equals 0. So now we're only talking about people whose GPA are 3 and public 0. So for a person whose parental education is 1, we would see the odds of applying is 2.05, right? So they're 2 times as likely to apply when the parental education, when their parents went to grad school. They're 2 times as likely to apply to grad school as well. If you want to compare that when par ed equals 0, right here, you see the odds of someone whose parents did not go to grad school, apply to grad school, is 0.713, so it's less likely to happen. If we take the ratio of odds, if we take 2.05 divided by 0.713, we get this number right here. Right? So we're saying that a person whose parents have a graduate degree are almost 3 times the odds than a person of applying to grad school than do a person without a parent's graduate degree. This thing is constant across the range of other predictors. This is what we can use to try to interpret our data. Right? This is true regardless of GPA, regardless of being public. This is the odds ratio, and it always holds. So that's where you see this used very frequently because it expresses odds relative, but it's the same across the entire metric itself. Now with probabilities, you can see the probabilities for each of this. When we got to bring this down, we have to keep these constraints. For GPA 3 and public 0, the probability of likely to apply is 0.673 when par ed equals 1 and 0.416 when par ed equals 0. But you'll note, if I were to change each of these values, these probabilities would shift because of the other betas, the other model parameters. So again, those probabilities, or the difference in probability, is subject to change. I'll show you a little bit more in another example when we get to interactions. Let's talk about public. Public, going back to the results, is beta 2. The value for it is negative 0.2006. Because public is a coded variable, we could talk about this as the difference in Logits for someone who went of being likely to apply to grad school for someone who was in a public university versus a private. So when public equals 1, we get this value. So it's telling us that people who are in public schools are slightly less likely to apply, but that's not significantly different. Right? So that is how we interpret it. We could also do the same thing. We could form odds, we could form probabilities, and so forth. Finally, let's look at GPA. Now, GPA we're going to treat as a continuous variable. Right? So it's quantitative. Right? So this is really a slope. This represents the increase, or in this case, the increase, it's significant, in Logit. So this is the change in Logit for every 1 unit change in GPA. So that means if someone's GPA goes up 1, means the Logit of their being likely to apply goes up by 0.54. So what does that mean? Let's go take a look. All right. So these numbers in here, again, come from when we zero out the other variables. Par ed equals 0, public equals 0. When we do that, we can see the probability someone applies to grad school as a function of GPA 3, right? Remember, this is GPA minus 3. So if we have 4, 3, 2, and 1, you see the probabilities they apply to grad school. So this is really telling us kind of the slope or the change in probability. And what you'll see is this blue line is how the probability changed based on GPA when the other 2 variables are equal to 0. And that's because this probability will shift if these other variables are not 0. So moving on. So in general, the linear model interpretation that you've worked on, that you understand from regression ANOVA, from the LM, still applies. It's just it applies to the logits. So you form most of the story that you tell based on logits. To interpret what's happening, we often switch to probability for predicted values or odds ratios for values that may be comparisons that we're trying to do. So when we have a model with two responses, remember we're in logits, we have to understand the direction of what's being modeled, and we talk about each of the terms continuously, just like we would in regular analysis, and sure enough, interactions are still going to be the same as well. And you know we get to interactions because this is sort of what this course is all about, is interactions. These are still going to modify or moderate the conditional main effects when they're in the model, and simple main effects are going to be present when the interacting variables are equal to 0. So let me show you an example where that happens to be. By the way, at the end of we get down to that example. Down here on line 114 is where you can find this. We're going to add to our model the interaction of parental education and GPA3. To do that in code, that just means we add this part to the model. We don't change anything else. Oops, pardon me. Add this part to the model. We don't change anything else, so you can see it right here in my code. And if I run this analysis, you can see the iteration history. It converged, hooray. First, let's tell whether or not this model improves the fit between the two. Let's go down here. We use our ANOVA function. We see that our likelihood ratio statistic is 1 with 1 degree of freedom, which gives us a p-value that is not significant. So we can tell right now we probably wouldn't want to interpret this model. We'd probably say that that interaction is not significant, and so we wouldn't go further. But for teaching purposes and to tell you about interactions and how they work in logit models, we are going to go for it. We're going to ignore it, and we're going to pretend it's significant and keep this model itself. Let's take a look. We use the summary statement. We see the interaction coefficient is right here. This is the interaction between parental education and GPA3. And now we can start talking about each of the parameters themselves, right? Because parental education and GPA show up in this interaction. That means that each of their beta weights right here, these are the simple main effects. And that's because they're the value of the effect when the interacting variable happens to be 0. And the value for public is just a main effect, or an unconditional main effect, meaning it applies to everybody. Still, like we saw before, we still have our threshold estimate here. Oops, pardon me. This, to get to an intercept, we still have to convert by multiplying by -1. So let's go through each of these and interpret what they mean. Starting with public, we're going to start with the unconditional main effect first. I'm going to show you a little bit of this and dive into it a little bit deeper using GLHT to form a linear predictor. So the first thing we want to know is let's find the predicted value in logits for someone who's at a public university, whose parental education, neither parents hold graduate degrees, and whose GPA is 3. So we're going to zero out all the variables. We're going to come up with that. And here is where we're going to see that. To do that in syntax, we can go back to our model. Start with our model. Here's our logit function. We have effectively an intercept. I'm going to keep it with -1 though, because I want to be able to remember I need to keep -1 for what we do in GLHT. Beta 1 times parental education, beta 2 times public, beta 3 times GPA3, and beta 4 times parental education, the interaction of parental education and GPA3. So if we're forming a linear combination of these values, we have to form a linear predictor that has 5 values, five terms to it. That's where that C function showed up before in our analysis. And each of those spots in C represent one value that multiplies each of the effects that we have. Beta 4, right? So what we want to do to form this predicted value for someone who is here, not in public school, not in public university, whose parents don't have a graduate degree with a GPA of 3, we would put a -1 for tau because it's got -1 out in front. So every time we want to put the intercept in, it's -1 in our example here. But the other terms would all be 0. And this corresponds to the slide previously. So I can go back to my R syntax and show you how this works. Actually, this is this right here is this is actually for someone who is at a public university here, right? So where public is 1. So if I flip over a slide where public is 1, public is this beta 2. So we're going to change this 0 to my eraser. Whoa, too much erasing. Change this beta 2 to a 1 there. There we go. So that's what's going to show up. So now we can actually code this. We do this in R. We'll see that our estimate is -0.5257. That's an estimate of the logit. Right? So that is a logit. We're going to see that that happens to be the sum of -1 times tau plus beta 2, which is what it was in that GLHT function to begin with. So what does that mean? Logits are hard to interpret. So what we can do for predictions, again, it's a prediction. We're just trying to see what is the predicted logit. Someone who is a GPA 3 in parental education, someone at a public university applies to grad school, convert that back to a probability. So let's do that, and the probability happens to be 0.374. Similarly, we can create the odds for this. Now, this is not an odds ratio. This is an odds. This is the odds of someone going to grad school, right? This is formed by that probability right here over 1 minus that probability. You can find that actually is an odds ratio. Pardon me. That is an odds ratio. So the mean differences. What we want to do though is test whether or not a person who's in grad school, who goes to a public university, if there's a mean difference between that and someone who goes to a private university. So now we're going to pull out the prediction of someone who where public equals 0. Going back to our value here, we make a 0 now for the beta 2 spot. We run this, and I show you all the effects here. So we have a predicted logit for someone who's in public school when GPA is 3 and parental education is 0, and we have a predicted logit for someone who's in private school. And you'll see these predictions, this is just telling you whether that logit's 0 or not. It doesn't really tell us much of an information here, so we don't really concern with that. What we're after here is the mean difference between the two. So, to talk about probability and odds, we can look into this a little bit more. Here, the probability happens to be the probability someone applies to grad school. For public is 0.37, and for private is 0.41. And you can see the odds for each of these associated. Now, these probability and odds are for GPA being 3 and parental education being 0. What about the odds ratio? The odds ratio comes from, we want to take basically the odds of public, odds of applying for public versus odds of applying for private. So what am I talking about here? I'm going to take, I'm going to call this public, right? Pub and pri right here. These are probabilities. So I'm going to form the odds for pub, and we're going to divide that by the odds for pri. Right? And what you'll end up seeing is that value happens to be this odds ratio of 0.83. So what we're saying is the person who is in public school has less odds than a person in private of applying to grad school. Similarly, we could just find that by the difference in the logit themselves, the slope, the beta weight that goes with it. So if I go back to that effect, in summary, where is summary? I don't have summary here. Go back to my R value here, and I go back to the summary for the model. If I just took this thing right here, we'd end up getting what I'm talking about. E of that value gives us a 0.83. So, which is this term right here. Okay. So now, to emphasize the point, odds ratios are what we use to really describe mean differences. Here's why. Let's imagine, probabilities depend on other predictors. That's the key, right? So the difference in probability between someone who's in public and someone who's in private school depends on the value of GPA and depends on the value of parental education. So now I'm going to let parental education be a 1 and GPA be a 3. I'm going to calculate these probabilities. Right? So if I do that, down here, if I let parental education be a 1, I put a 1 for that beta weight now. And you'll note still I have zeros for GPA and the interaction. Now let's combine all of our effects. Here are our Logits for those predicted values, right? So this was the public and private for someone with GPA 3 whose parents did not have a graduate school degree, so parental education of 0. And this is the predicted Logits for the same people, but those bottom two have a parental education where at least one parent went to grad school. So yes, the Logit values have shifted. That's okay. That's not a big deal, but let's convert those to probabilities though, right? So converting those to probabilities, what we can see is here are the probabilities for each of those 4 groups. So the probability of being in applying to grad school, likelihood to apply to grad school, these are the 2 probabilities we saw before. The new probabilities are 0.654 and 0.694. But here, let's take a look at the difference in probabilities though. The difference in probabilities that we would have before, when parental education was 0, is 0.043. And the difference in probabilities now, when parental education is 1, has shifted slightly. Now it's in the 3rd decimal place here, but that's part of the reason is because we don't really have a significant effect of this. The beta that we're adding here is not that big. So you don't see that big of a shift, but it is a definite shift. So we can't really say the difference in probability without honing in on conditioning on each of the other variables themselves. Similar to that, the odds themselves, if we were to take the odds of each of these associated probabilities, you see the odds shift. Right, so here are the 2 odds we saw previously. Now the odds are a little bit different. And again, the difference in odds would be different if we just subtracted them. But really what doesn't shift, though, is the odds ratio. If I took 0.59 and divided by 0.71, we get 0.832. And if I took 1.89 divided by 2.27, you see the same odds ratio. So odds ratio doesn't shift. Right? What would we do here? We allowed one of the other predictors to change. And we saw that the difference in probability shifts. It depends on the other predictors. The difference in odds, a subtraction, would shift. But if we took the division, if we took one odds divided by the other, that does not shift. So it's sort of this relative proportional, well, sometimes we call this proportional odds. The odds are proportional across the model itself. So that's why we often use odds ratios to describe effects. Odds ratios, I think, are just as confusing as Logits, though. So, but I will say odds ratios are also there's a conversion. Those are effectively effect sizes that we're looking at too. Okay, now let's go into the interaction. Okay, so this is where things get really crazy or fun. Actually, this is actually more fun than crazy, in my opinion. You guys, imagining you're arguing with me on that. But let's take a look at our effects again. We're going to take a look at the mean difference for parental education, right? So that we would start with this main effect. But remember, this main effect is a simple main effect, meaning it's conditional on for a person whose GPA is equal to 3. We have to zero out this GPA difference because parental education shows up on it right here. So that's the same steps I'm taking here are the same steps you took to evaluate interactions in a regular linear model. So, moving down, let's talk about looking at the mean difference in Logits for someone whose parental education is 1 versus a parental education of 0 when GPA equals 3, right? This is what we're after. So let's go and figure out the model itself and try to work through what those equations are. What is the predicted difference in Logits between these 2 types of people? right? So again, for the person who predicted logit for someone whose parental education is 0 and GPA is 3, we go up to our model. We have GPA 3. It zeroes out this thing and this thing, right? And we're left with parental education. I am screwing up my notation here. Parental education. Public is still around, so we actually have beta 2 public here. And parental education is 0, so this goes away too, right? So this right there, it goes away. And let's go with the person whose parental education is 1. Again, GPA 3 gets rid of this and this, but we still have beta 1 and we still have beta 2 public. So beta 1 is there. I'm going to plug a 1 in for parental education, and we'll have beta 2 public right here. So if I were to compare these two, if I were to take the difference between parental education, this bottom one and this top one, the public would go away. Beta 1 didn't show up here. The thresholds would go away, and we would be left with that beta 1 that we saw in our analysis itself. So now going back to our R syntax, where I actually did code this correctly, really what I'm after, if I want to go and figure out this mean difference, I can actually go and create each of these predicted values in Logits. And that's what I'll do here. Here's the predicted value for someone with a parental education of 1, GPA 3, and public being 0. And then I can compare that with the parental education of 0 for the same type. And you see the difference in Logits for either. So if I were to take the difference in these two, I could just take the difference in my linear predictor. Oh, that's a little weird. And I would get this, right? This is basically the difference. We would have a 1 for the beta 1 spot and zeros elsewhere. So putting that in, you'll see that linear combination. And of course, I labeled that correctly. There we go. The difference here from the R output, you see that here's the predicted value for Logit for parental education of 1. Here it is for 0. And so this value minus this value gives us 1.16, which sure enough comes from the estimate itself. So what we would say is that a person who has GPA 3, so this effect only applies for people who have a GPA of 3, we'd say the difference in Logit would be 1.16. And again, we could talk about what that means with respect to an odds ratio by taking e to that number if we wanted to. But it'd be very hard to talk about that with probability because we'd have to condition on the other variable, in this case public, to make it work. So let's move forward here. Let's talk next about what happens to the slope. What we want to find is the slope of the model. The slope, in this case, the slope for GPA 3, or the main effect of GPA 3. Talking about this thing right here. This is a simple main effect, right? So that is the slope that says for every 1 unit increase in GPA 3, a person whose parental education is 0, right? Knocking out this part right here, they have an increase or a difference in, or for every 1 unit increase in GPA, the Logit goes up 0.6567. But where do we get that from? Again, let's go back to our model. Here we have it. What is the slope for GPA 3 when parental education is 0? Now, again, we're talking about slope for GPA 3, so we have to figure out all the places where GPA 3 shows up. Those are the two possibilities right there. But parental education 0 knocks this one out, so we're left with beta 3 GPA. So the slope is beta 3, the main effect, simple main effect. What about when parental education is 1? Well, again, that now brings this part back into the analysis right here. So that would mean that we have beta 3 times GPA 3 from the simple main effect and a beta 4 times GPA 3 from the interaction. So we combine like terms, we see the slope is beta 3 plus beta 4. And so the difference in slopes between parental education of 1 and parental education of 0 actually comes from beta 4, right? The beta 3's cancel. So going into this, we can actually see that with our analysis right here. I can get the slope for either. Here are the two slopes we saw. It was positive for a person whose parental education was 0, it was negative for parental education of 1. Now, if I were to create the difference, now I'm just creating this by taking my little matrix of zeros and ones and subtracting it, right? So this is really giving us that beta 4, that interaction coefficient. So here, this turns out to give us the difference in slope, which actually is the interaction. Now, the difference is not significant itself. That's how that happens to be, and this right here is negative 7588 right there. So there you have it. Okay. So moving forward, this now will help us, because what we can talk about is the differences in means. How do the means change for any level of GPA? Let's interpret that interaction, right? So we saw the mean difference previous to this was 1.16. The label on this is bad too. 1.16 was our mean difference. That was what we had found right up here. Our mean difference in GPA. Whoa, something's going on there. I'm sorry about that. There we go. The difference in means was 1.1608 right there. So that tells us where the mean difference was when GPA was 3. But how does that mean difference shift for every additional unit of GPA? Well, let's go back to our model. So here, what is the mean for parental education of 0 for any GPA? Well, parental education of 0 knocks out that one, and knocks out that one, so we're left with this mean predicted logit. What is the mean for parental ed? Equals 1 instead of 0. No? For parental education of 1, we can put this part back, and we need to put in our interaction as well. So now what we end up with is this right here, basically all the parameters. So if we just subtract the 2, we take off tau 0, we take off beta 2 public, and we take off the beta 3 from here. What we see is the general mean difference is beta 1 plus beta 4 times GPA, right? So when GPA was 3, the mean difference was given by beta 1. But for every 1 unit change in GPA, the mean difference changes by beta 4. And that's what we end up seeing right here. So what is that mean difference? Well, that is negative 0.7588. So as GPA goes up 1 unit, the difference in mean shifts by negative 0.7588, or if we talk about the language that we saw in a previous homework, beta 1 was the mean difference. Beta 1, the mean difference was 0.1608 right there. So that was positive, and when GPA goes up 1, this comes down by negative 0.7588, so it becomes less positive. So now let's go to the very end of my R output here, and what you can see is what we can do is describe where the mean difference between parental education lies for every level of GPA that we'd like to build. Right, so here are my output terms. I've used this functional equation right down here, and I've plugged in values of GPA. I've plugged in GPA at 0, 1, 2, 3, and 4, and that corresponds to GPA. So this is GPA. So GPA 3 was negative 3, negative 2, negative 1, 0, and 1. So I plugged in each of those. You can see the last term on there for that. And you can take a look at my mean difference. And so here's my mean difference in Logit. And what you'll find is the only place where I found a significant difference in Logit was actually at GPA value of 3. Otherwise, people with parental education and people who had a parent who went to grad school versus not, were not significantly different in pretty much all the other places, although it's starting to approach that way in the 2 area. So sort of an interesting finding, right? Not only is the mean getting different, right? You can see the value of the mean is becoming less positive as we go forward. The standard error is shifting as well, right? And the smallest standard error we find is right there at the simple main effect, but then it's increasing as GPA goes up as well. So that's it. to wrap up, what we have here is that general linear models are necessary when we have not normal data or not normal outcomes, in this case a binary outcome. But the big picture to think about is most of the interpretation remains the same, particularly when we deal with logits. Instead of saying now the outcome changes, we're saying the logit of the probability of the outcome changes. Then to describe it better, sometimes we use odds, sometimes we use probabilities, or odds ratios, pardon me. Odds ratios are great for describing how kind of the difference between two different predicted values or predicted logits would be. Probabilities are great for giving a sense for different predicted values overall. We can't use probabilities, though, when we were taking differences because they depend on the other values of the predictors as we go forward. So it's sort of this added complication, but it all starts with the core that you already know, and that comes with the logit. So if you hang on to that to begin with, translating it becomes a little bit easier. So that's it for this recording. Hopefully the sound kept on this one, and we can keep going. I will leave you for now.